Hi, this presentation is the second of three providing background and context for the study of computer hardware. This part is concerned with the developments in electronics that have underpinned the dramatic advances in computer hardware of recent decades, and particularly features Gordon Moore and his famous law that describes the rate of increase in the numbers of transistors available on a computer chip. It starts with a quick look at basic CMOS technology, and then goes on to track the developments from early logic gates through to modern processors in their various implementations. It finishes up with where we are now and some guesses for the future. So, starting with CMOS, computer hardware development is fundamentally about transistors, and one sort in particular, complementary metal oxide semiconductors, or CMOS. The complementary bit means that there are two different types of transistors working together here. NMOS transistors operate with N for negative charge carriers, electrons, to carry a current, and PMOS transistors use P or positive charge carriers to carry a current. A PMOS transistor has two contacts of P-type silicon with positive charges sitting on a block of N-type, with a metal control gate in the middle insulated by an oxide layer from the N-type block. If a negative voltage is applied to the gate, it will attract positive charge carriers towards it, and when they accumulate under the gate, they link the two N contacts to form a continuous conducting channel of P-type positive charge carriers, and a current can flow. The device acts as a switch controlled by the voltage on the gate. If the gate voltage is positive or high, the switch is open, and if the gate voltage is negative or low, then the switch is closed. On the circuit schematic diagram, this is indicated by the small circle on the gate connection to indicate that a low voltage on the input closes the switch. An NMOS transistor is the mirror image, with two N contacts of N-type silicon sitting on the block of P-type. This time, a positive voltage on the gate will attract electrons to form a channel linking the N contacts, and the current will flow. So the device acts as a switch that closes when there is a positive voltage on the gate terminal. The on-off operation of these switches can be used to build digital circuits that can be described by Boolean algebra. This slide shows a CMOS inverter circuit, the P-type transistor at the top and an N-type below it. Now, a negative voltage applied to the input appears on the gate of both devices. The PMOS transistor will switch on, and the NMOS transistor won't. And so this connects the output to the positive terminal as shown in figure A. However, a positive voltage applied to the input, and hence to both gates, will cause the PMOS transistor to switch off and the NMOS transistor to switch on. And this will connect the output to the negative terminal as shown in figure B. The overall result is that an input signal that changes from a negative to a positive level will cause the output to switch from a positive to a negative value. The circuit has inverted the input signal. It only then remains to label the negative level as 0 and the positive as 1 to give a Boolean logic inversion operation. This slide of a logical NOR gate shows how more complex CMOS logic functions can be built up. The top half of the circuit is made up of PMOS transistors that switch on when their input is a logical 0. Their function is to connect the output to the positive supply terminal, or logical 1, and they're known as pull-up transistors since they pull the output up to 1. The truth table for the required NOR function shows the output Y is 1 when input A and input B are both 0. By putting two transistors in series so that both A and B have to be switched on to connect Y to 1 achieves this. And now the top line of the truth table has been built. The output is pulled up to 1 when both inputs are 0. The bottom half of the circuit is made up of NMOS transistors that switch on when their input is high, or logic 1. Their function is to pull the output down to 0. Now, by checking the truth table, it shows that the output must be 0 when either A or B, or both together, are 1. And putting the transistors in parallel achieves this, since if the gate of either A or B is 1, that will short the output down to logic 0, and so completing the truth table. A similar strategy can be used to build more complex logic functions. However, the most important features of CMOS technology are, firstly, that it's possible to construct hundreds of millions of these simple devices on a very small block of silicon, and secondly, that inspection of the circuits shows that the circuit doesn't draw a current in either of its two stable states, since either the top half or the bottom half is always switched off. Power is only dissipated owing to leakage or switching between states, and this is extremely important for high-density modern chips. So CMOS transistors made it possible to build logic gates at increasingly high densities as fabrication technologies advanced. Moore's law tracks this progress for the Intel processors on the slide, showing an increase of 6 or 7 orders of magnitude in the past 4 decades, from around 1,000 in the early 1970s to approaching a staggering 10 billion. The path from simple logic gates like the NOR gate in the previous slide to complex integrated systems started with the basic 7400 series TTL and later CMOS logic families. These were capable of integrating typically between 1 and 8 individual gates on each chip using 14-pin Julian line packages. The next stage, after fixed logic functions, came with programmable logic arrays, or PLAs, introduced by Texas Instruments in 1970. Logic minimalization Karnaugh map type techniques can bash any combinational logic function into the form y equals a and b, or c and d, or e and f, and so on, that can be built up out of simple AND and OR gates. So the PLA comprises banks of ANDs and ORs with a connection matrix to enable the required logic function to be programmed, either at the factory by final metallization, or locally by fuse blowing of the interconnects. By the early to mid-70s, device count had got up to a few thousand transistors, enough to build a small computer central processing unit. Intel marketed the 4-bit 4004 and 8-bit 8008 chips before producing the first widely usable device, the 8080, in 1974. At the same time, the device count and complexity of straightforward logic chips was also increasing. The lattice programmable array logic, or PAL, introduced in 1978, followed the PLA pattern, which included a read-only memory chip rather than fuses for one-time programming by users. These devices developed rapidly in complexity, adding registers and output macrocells with various functions and added flexibility. As the devices increased in complexity, it became convenient to use ECAD design software. Early hardware description languages, or HDLs, such as PALASM, that converted Boolean algebra functions into fuse maps for blowing the chips. Early processor and logic chips were constrained by packaging and pin counts, requiring multiplexing buses and other strategies to free up pins. Packaging, though, had also moved forward with pin grid array, ball grid array, and variants, utilizing the whole bottom surface of the package to provide pin counts to match the 64-bit wide buses of modern processors. And also options were being developed for integrating entire systems to incorporate analog circuits, machine mechanical sensor parts, or MEMS, and system-in-module or system-on-module packages combining discrete and integrated components. The next incremental stage in logic development was generic array logic, with yet more macrocells, registers, and so on. Its key features were erasability and programmability in the field for rapid prototyping. And following on this line of development provided the current range of complex programmable logic devices, or CPLDs, with tens of thousands of gates, midway in complexity between PALs and the FPGAs coming next. They were structured into macrocell building blocks with combinational logic arrays feeding a number of sequentially clocked registers, along with additional specialized functions such as integer arithmetic. They have limited flexibility but predictable timing delays, and a high logic-to-interconnect ratio. They include non-volatile memory and so are useful for system startup for configuring volatile devices like early FPGAs. FPGAs are very widely used, highly functional devices, first introduced by Xilinx in 1985. They contain millions of gates and are capable of implementing complex systems on chip. The basic architecture is that of programmable logic blocks with reconfigurable interconnects. Modern devices contain advanced functions such as adders, multipliers, memory, and even complete dual-core ARM processors, as implemented in hardware in current Xilinx and Altera chips. Alternatively, software processor cores can be programmed along with other functions as part of the user development process. FPGAs are basically volatile devices, often requiring external flash or a CPLD for their configuration, although devices now can store their configurations internally in non-volatile flash memory. They're very flexible and can be reprogrammed in the field and on the fly, leading to the concept of reconfigurable hardware, devices that can change their internal organization according to the processing demands at the time. They're usually designed using VHDL or Verilog synthesis tools, and that is, the functionality of the design is described, simulated and verified in a high-level hardware description language program before being directly synthesized to the chip. ASICs are essentially totally customizable designs that are built on bare silicon with precisely the components required for the given application. They can be very high complexity systems on chip with perhaps 100 million gates and many different processors, with applications including smartphones, televisions and cameras. However, to design such systems from scratch is extremely expensive, and in practice companies have pre-designed subsystem components that can be assembled into larger systems to minimize the design effort. Companies like ARM have concentrated on the design of computer processing cores rather than the production of processor chips. They license the designs for others to incorporate into their systems, and provide complete platforms including a wide range of supporting peripherals to support the basis of a system-on-chip ASIC. This is a somewhat similar approach to that used in discrete microprocessor designs of the 1970s, but by integrating software on the chip rather than as discrete devices. The processor designs can be in the form of a netlist of gates that can be directly synthesized to a particular fabrication technology, or as soft or intellectual property designs in VHDL software that can be tuned and ported to a variety of different hardware implementations. Taking a look then at the current situation for computer hardware electronics. In terms of sheer device count, Moore's law has pushed about this far. More transistors fit in chips with regular structures like ROM or FPGAs than general-purpose processors. And these transistors support a very wide range of different processor architectures. Microprocessors are general-purpose PC-type computer central processing units on a chip, which have continued to increase in performance. Increasing device counts have prompted a move to multi-core designs, imposing a challenge to software designers to make best use of this parallelism. Web servers face an inherently parallel task requiring wider collaboration, and these have developed additional functionality for coordinating large numbers of cores on chip, and with non-uniform hierarchical access to memory and resources on other chips. Current processors include HP, Intel, Itanium, Xeons, and AMD Opteron models with up to 16 cores. IP, or intellectual property cores, are processor designs that are sold as software licenses for integration into other products, such as the ARMs inside Apple iPhones and most other mobile devices. Microcontrollers are complete self-contained computers on a chip, designed for embedded instrumentation and control applications containing memory and I/O functions such as pulse width modulation for driving motors. The emphasis is on low cost and low power consumption. Current devices including the AVRs that form the basis of the popular Arduino range of single-board computers. Graphics processors, or GPUs, are highly parallel, with many cores and floating point units to match the parallelism of computing picture elements in a frame. As graphics processing demands have become more sophisticated, these processors have become more powerful, and capable of an interesting synergy with conventional processors for high-power processing tasks. Current devices include NVIDIA Tegras and AMD Radeons. Digital signal processors, or DSPs, typically perform repetitive filtering type operations on streams of data. They're optimized for multiple data applications using very long instruction words and Harvard architectures, with execution units designed for multiply-accumulate calculations. Current devices include Texas Instruments 6000 series and analog devices Sharks. And these are also moving to a synergy of specialized along with conventionally integrated ARM processors. Hence, electronic hardware can deliver the functionality required for computing in a wide variety of options with a spectrum of hardware and software programmability. The application concerned will determine the best approach, particularly in matching the design complexity and estimated production run to the device development risks and costs. In general, integrated solutions have the lowest volume production costs, but development costs can be very high. This can be mitigated by using proven license platforms, but there may still be risks in integrating these with in-house design components. The main options from there are in the balance of hardware and software design required to configure the required functionality. Hardware is generally more expensive to design, fault find and update, but it provides a solution with smaller chip area that runs faster and is cheaper to produce in quantity. Software is cheaper and easier to design and flexible to update, but it generally provides solutions that run slower and occupy greater chip area. General and special purpose microprocessors have fixed hardware, and their functionality is defined by software. But it's unlikely that a particular application will fully use a general purpose processor, since it will be designed to fit as many applications as possible. But they do provide a ready-made hardware solution at known cost and availability. At the other extreme, ASICs are a blank canvas on which any hardware and accompanying software can be drawn and tailored precisely to the application. It's however common for some of the hardware at least to be licensed IP designs sitting next to new and reused in-house components. CPLDs and FPGAs occupy the middle ground, as they comprise ready-built hardware that's customized by wiring the components together via reprogrammable interconnects. FPGAs are popular, particularly for prototyping, as a way to produce complex application designs at lower cost than ASICs, using VHDL synthesis tools. But it may still be a problem to match the hardware capacities available precisely to the needs of an application without wastage. Most of these applications have sufficient complexity to incorporate one or more, typically ARM processors, either as pre-configured hardware in DSP, GPU or FPGA chips, or as software for implementing on an FPGA or ASIC. And equally, it's possible to buy an ARM-based computer on a chip from a licensee, for example the Raspberry Pi, a functional computer at a fraction of the cost of a PC. Looking back now at Moore's law, it's apparent that device count is not the only issue though. Despite increasing transistor numbers, overall computer performance has leveled off recently, in part owing to power dissipation problems preventing increases in clock rate. But it would also seem that it's becoming harder to improve performance by improving computer architecture, and manufacturers have used many of the extra transistors to move to multi-core chips, although this too has not had such an immediate effect on performance. So where are things going? At present, fab is moving towards atom-scale technology. Device count is heading into tens of billions, and although silicon is fairly cheap, fab plants can get pricey at several $1 billion a throw. The issues arising are firstly how to continue with the Moore's law. Well, in addition to the power war, the limits are imposed by the speed of light on carrier mobility and the wavelength of light on fabrication lithography. But roadmaps seem set fair at least for the next few years. Quantum mechanical effects begin to cause real problems at these atomic scale feature sizes, and the hard limit at somewhere near 2 nanometer feature size is predicted. Interestingly though, a single phosphorus atom transistor has already been demonstrated, although its operating temperature of -196 degrees could be a problem for office use. Then there's the problem of reducing power dissipation and the associated issue of fully exploiting parallelism in multi-cores and multiprocessors. Fabrication has generally advanced ahead of design and verification capability. That is, it may be possible to put 10 billion transistors on a chip, but it's quite hard to get them to do useful things, and even harder to check if the resulting design will work fully. In turn, this leads to issues of design reuse, ECAD design tools, and how best to integrate designs from different sources onto one chip. There doesn't seem to be any lack of new ideas. This slide shows some of them. Firstly, in the continued development of present technologies of the use of more exotic materials and transistor structures, coupled with developments in packaging and moves from planar towards 3 dimensions. Then, looking further forward to non-silicon futures, there are carbon nanotubes, molecular devices, DNA coding, and quantum mechanical devices, and who knows what else over the horizon. The final part of this series of 3 videos looks at the contribution of computer architecture and organization to increasing performance, starting from the original von Neumann machine up to the present day.